So I'd like to next look at the entropy change in reversible processes. And we've already discussed the Carnot cycle and that it's an idealization of reality. It's the best possible way that a heat engine can perform. And it's got two steps that are reversible and isothermal, and two steps are reversible and adiabatic. Okay, so let's see if we can analyze those two steps. So first of all, let's look at the adiabatic steps. For the reversible and adiabatic, dq is 0, but delta S is going to be the integral of dq over t, right? Well, if dq is 0, then delta S has to be 0, which means that reversible and adiabatic is the same as saying isentropic. And what's really nice about this is, in fact, if I have any two of these words, the third word applies. So reversible and isentropic will imply it must have been adiabatic. Or, one's a little weird, isentropic and adiabatic would imply that it's a reversible process. Now, my other type of steps that I have in the Carnot cycle is these isothermal reversible steps. Now, if it's isothermal, dq over t is more easy to integrate because t is constant. I can bring it out of the integral, and so it's just q over t. And so I have a way of evaluating the amount of entropy change as the amount of heat transfer divided by the temperature it happens. Now, one of the interesting things about this is if you were to do a plot of temperature versus entropy for the Carnot cycle, dq is TdS, right? That's what we've said. dq is TdS. And so if I were to think about that, that would be like saying Q is the area under the curve, T versus S. So therefore, in the Carnot cycle, the two heat transfer steps, it's the area under the curve. Now, QL, if it's an engine, is going backwards, so it's negative. QH is going forward, so it's going to be positive Q. So I get the signs as expected relating this to area. But the other cool thing is that the area between those two curves, which are straight lines in a Carnot cycle, is going to be the net heat transfer, but that's the net work. And so the area inside the rectangle divided by the area under the top curve, the high temperature heat transfer curve, will be the thermal efficiency. And that as we play with the temperatures, we would actually change that thermal efficiency, which does relate to the Carnot efficiency 1 minus TL over TH. Other thing that we want to do before we can really move on, this is a very, very important result, but it's going to be something that we're going to use as a tool to derive equations more than what you will use to calculate intermediate results. But it's a very useful one, and the idea is let's look at a closed system first law problem without potential or kinetic energy changes. So I'm going to envision a very special process, okay, no kinetic or potential energy changes, and I'm going to say that, this is a reversible process. So if it's reversible, dq is TdS and dW is PdV. So I can plug those in and I end up with this. Now up here the first law was path dependent because it had those path dependent pieces Q and W, but now I've eliminated the path dependence and this is all just properties. So this is generally true despite what crazy path stuff I selected up here. So TdS equals du plus PdV is always true, skipping all that stuff up there. Okay, now this relates S to U and V, which I could look up in tables. A lot of times though we have H, and so if I wanted to use U as H minus PV, taking the differential of U, I get the differential of H. And then I need to do a product rule on the PV term. So minus PdV minus VdP. But if I substitute this in, for the du right here, I end up with the PDV and the minus PDV canceling, leaving me with this expression here. So, real processes, does this have any application? Well, in fact, it does, because the process that I selected was crazy reversible, not real. But I ended up with something that was path independent, and so therefore I can apply it to any process. Now, most of the time what I'll do is I'll take this and use it as ds equals, because then I can use this as a calculation tool for finding delta S. So it's dH over T minus V over T dP, D over U over T plus P over T dV. So we're going to be looking some more at this in the next several videos.